you have your blue notes? The improper integral lesson, part 1. This is part 1 of 2. There are 2 types of improper integrals. They both involve unbounded behavior. One type today is an infinite limit. You will maybe take the area, you'll take the area under a curve from 1 to infinity of some function. That is an improper integral because the region is bounded, it's unbounded. Another later is a discontinuity case. For example, if you did from 0 to 1 of 1 over x dx, on the surface it doesn't look improper, it looks like your normal integral, but the gotcha to that is 1 over x isn't continuous at surface. Diverse classic right there. So you have unbounded behavior at the x. So those are improper integrals, and this is definitely one of those cases where I am super picky about the work. Any math person is. Those of you in AP Physics, Mr. McCall, in AP Physics, you will have to deal with improper integrals, and his job is to deal with the physics, not the calculus. So he will do math that makes me we'll just leave it at that, okay? But the point being, on AP Physics, they don't grade you for proper math. In AP Calculus, they grade you for proper math. It's math class, for Pete's sake. Would you grab your calculator, please, if you put it away? And let's go with, first of all, I would like you to see the bounded area part of your calculator. So would you, reading these here directions, actually I'm going to clear my scratch pad. Okay, would you put in 1 over x into, oops, what the cock-a-doodle, what happened there? Did I hit 1 enter? I did. Excuse me, 1 divided by x. Okay. Would you change your window, please, to 0 to 10 in x, and negative 0.2 to 0. I can't see, I covered it up. 0.5, is that what I said? Yeah. 0.5 in y. So there's a zoomed in kind of form of the 1 over x curve. You follow? Now what we're going to get into is, if you take the area under this curve going further and further out to this tail, as you accumulate more and more area, do you approach a limit and therefore your answer is a number? Or does it just keep growing without bound and your answer is not a number, it's infinite? So let's see. Would you go to Menu, Analyze Graph, and go Bounded Area? If your calculator is not updated, it might not show bounded area, but you should have bounded area, yeah? The first graph we're going to bound with is the curve itself. The second graph is the axis. The lower bound is the bound of the integral, which is 1. You can just type in 1, enter. And the upper bound, we're going to start by going to 10. The calculator then shades that area and calculates it. And I'm getting a bounded area of 2.305. So if I went from an x of 0 to 10, then the area from 1 to x over, I'll call it 1 over t, is the area I got was 2.302. Did I go too fast, or are you with me? Are you cool? All right. Now, we could continue to do that. We could change our window to 100, or we could just go back to the way we normally do it, which is in the home screen. Say we did the integral, shift plus, from 1 to 100 under the curve 1 over x. Then my area is 4.6 0.05. Let's send that tail a little further up. Go to 1,000. I get 6.907. Now I was hoping that I would start to see a limit. Does it look like we're reaching a top floor? It does not. To me. Okay? Now let's say then that should we do a table here? Okay, so I'm going to jump around a little in the notes. Stick with me, okay? The problem seems to be that I'm adding more and more area, and that area is too big. I'm adding infinitely many. So think like a geometric problem where you're adding more things, but the things aren't getting small fast enough. Now let's say we played around with this a little, and instead we jump down to the second graph, which is 1 over x squared, and see if this starts to approach it. Now, because we're squaring, the areas we're going to add are going to get smaller faster. And so I'm hoping that maybe with that, it'll converge. So let's try, instead, the area under 1 over x squared, gradually speaking, from 1 to 10 first, of 1 divided by x squared. And I get 0.9. You get 0.9. Yes? Now try doing that same calculation, but now going a little longer down the tail towards 100. Those of you in AP Stat, these are all those normal curve areas and probability density functions. Those were improper integrals. 0.9. If you guys go on to be mathy people or engineers, really, you'll take calc-based probability and statistics. It's pretty great, really. It's awesome. I love it. If you go from 1 to 1,000, you can see the pattern. It is starting to approach a limit. It seems like this is approaching a limit of 1, despite the fact that they're both dealing with this infinitely long tail situation. Now, this, to me, first and foremost, is so wicked cool. Because really, if you were to interpret that, that means if I take this region from 1 there and tried to calculate it, the area under 1 over x, yeah? That it's infinite. It can't be found. You with me? But if you were to revolve this around the axis, making a volume of revolution, then that finite area would have, that infinite area would have finite volume. Yeah, isn't that crazy? And furthermore, if you had surface area, there's something called a surface area. Besides volumes of revolutions, you do surface area. This figure created, I couldn't paint it because it would take infinite paint, but I could fill it with paint because it has finite volume. Yeah, I could fill it, but I couldn't paint it. Now that, no, what? Obviously, I'm going to great.
If you can fill it up all the way, why can't you just paint it?
Yeah, outside. We'll show you. Let me show you, shall we? Okay. So, if we were to do this with calculus, it is the limit or the area from 1 to infinity under the curve. Yeah. Now I'm talking. The first curve was 1 over x. All right. That's an improper integral. To see what this approach is, anytime you're talking with infinity, you're saying the upper limit grows without bound. Infinity is more of a verb than a noun. You're doing something. You're getting bigger without bound. You're not there. Infinity is more of a process, getting bigger. Now, that said then, as it grows without bound, we really want to know as this thing, this upper limit, I'll call it A, gets bigger and bigger, what happens? Well, that really means as that upper limit approaches infinity, what does the area under the curve approach? This is the first step in an improper integral. That is required. It is not an option. It must be done. What is then the antiderivative? We'll do the limit later. We need to figure out the integral first. What's the antiderivative? Log of x, and I'll dump the absolute value because we're in the first quadrant. The antiderivative then evaluated, or at least, in other words, the fundamental theorem of calculus says this is the same as log of a minus log of 1. Well, now we can evaluate the limit. Log of 1 we know goes to 0. As a goes to infinity, the log of a goes to, if you put bigger and bigger things into log, you get bigger and bigger. So this is infinite, which is to say it diverges. It doesn't reach a finite limit. And now if you do that same process on the other one, you'll see a little different antiderivative. This guy is the same as the limit as a goes to infinity from 1 to a of 1 over x squared, which I know you guys wouldn't make dumb mistakes, but I typically make power rule mistakes when it's negative exponent, so I'll take the time to rewrite it as an exponent so I don't screw up the power rule, right? As, are we recording this? Yeah. All right. As a goes to infinity, what's the antiderivative of x to the negative 2? Raise it by 1, divide by the new. Negative 1 over x, isn't it? X to the negative 1 over negative 1. Okay. 1 to a. If I evaluate at the limits, here, the antiderivative not being log like the previous one is going to be make for a different result. I have negative 1 over a plus 1 over 1. As a goes to infinity, what does 1 over a go to? 0 plus 1. That has volume of 1. Now, this to me is the part that is going to cost you points in the homework and get me really frustrated. You would never integrate from 1 to love because that's ridiculous. That's stupid. It's an idea. It's not a number. What would that be? The natural log of love? That doesn't mean anything. And so you will never say this is the natural log of it. No, no, no. You will use a limit. Okay? Or you and I will be enemies. Understood? I don't hear understood. Do you understand?
Oh, yeah.
That's better. Okay. You don't want to be my enemy, baby. All right. So go to the back side. I'll show you exactly what I want to see in the work. We'll do the first one together. You'll try the other three. You'll start to get a feel for it. Then we'll get some little bit of variation on it, and then we'll be good. So say this first one. The very first step is to rephrase with a limit. The limit as a goes to infinity. A is arbitrary. You could use whatever letter you want, a variable you want, from 0 to a, 1 over e to the x dx. All right? So you make the improper integral proper with a limit. You then anti-differentiate. The limit does not get touched until the very end, so rewrite it. Be careful there. What is the antiderivative of e to the negative x? Negative e to the negative x, or negative 1 over e to the x. Remember, that's not really e to the x, it's e to the negative x there. From 0 to a. Then use a little fundamental theorem of calculus, which is to say you show how to evaluate a definite integral at the upper, minus, which makes this plus, at the lower. And then finally, you're ready to evaluate, well, what happens as that right-hand limit gets infinitely large? 1 over e to the a goes to 0. 1 over e to the infinity would be 1 over huge, which is 0, plus 1 over e to the 0, which is 1. So your answer for that area is 1.
No, they don't always come out to be 1.
Okay, try the other 3. How are we doing? You get negative 1/2 for the first? infinite for the second or third one. Okay. Notice how I hope that you see a little bit of compare and contrast in the two. Just the smallest difference on this side of x to the first in the denominator, x to the negative one, if you like, makes all the difference. Because when you raise it by a power here, you end up in the numerator, it gets infinitely large. But when you raise it by a power here, the antiderivative is still in the denominator, you're going to converge. So 1, that power of 1 in the denominator is the great dividing line, really. So, a goes to infinity. X to the negative 1/10. Negative 1/10 from 1 to a. I make lots of mistakes on my antiderivatives, really. So this is negative 10 over the 10th root of a plus 10 over the 10th root of 1. That goes to 0 plus, right, 0, sorry, I didn't be right. 0 plus 10, so that one can be.
Negative areas with this?
What?
We can get negative areas?
Yes, absolutely. I know I started by introducing it as an area problem, but let's, and I can't remember, I've talked to somebody with this. Remember the difference, especially in algebra, or Calc 1 problems, the difference between this problem versus this problem, the area enclosed by y equals x squared minus 4 on the x-axis. Okay, there's a ton of overlap, obviously, between the two problems. But this, there's nothing in here about saying it has to be positive. It's just the signed area. So this would be a negative answer, and that's fine, because there are a lot of problems where integrals should be negative, velocity and so on. This, if it says area, then that should be positive. Now these are just straight up integral problems, so negatives. Okay, let's go on to this guy. Emma and Harper start back to back at 0 on the number line. They walk away from each other. What is the average of their positions as time goes to infinity? 0. Okay, 0. Anybody else? Okay, nobody wants to be correct. Infinity. Okay. What else? Yes, there you go. Depends. It's indeterminate. Depends on how fast they're going. Now that is the idea behind the great gotcha, one of the great gotcha calculus problems of all is that indeterminate form, negative infinity, or sorry, that improper integral, negative infinity to infinity of x dx. Now, this is kind of throwing it to the wolves here because this is actually improper on 2 parts. It would make sense to students want to say let a to go to negative infinity and let b go to positive infinity, and from a to, that's not a thing. You don't take the limit of it. You don't do that. Okay, so I understand what you're saying, but that's not. Instead, goes something more like this is equivalent to the integral from negative infinity to 0 is logical, but it doesn't even have to be 0. It could be any in there. X dx plus from 0 to infinity of x dx. Then you make a limit statement for each. This then is the limit as a goes to negative infinity from a to 0 of x dx plus the limit as b goes to positive infinity from 0 to b of x dx is the proper way that that should be set up and done. The limit as a goes to negative infinity of 1/2 x squared from a to 0 plus the limit as b goes to positive infinity of 1/2 x squared from 0 to b. The limit as a goes to infinity of 0 minus a squared over 2 this should be negative. Plus, the limit as b goes to infinity of 1/2 b squared minus 0. Well, what does this approach? Infinity plus or negative? It's minus positive. The a squared is positive, so negative infinity squared is positive, huge, but it's being subtracted. So it's negative infinity plus positive infinity, and we know infinity minus infinity is indeterminate. Because the rate matters. Yes?
Why can't you just do limit as a goes to infinity from negative a to a?
From negative a to a. Oh,
You would still get
because you don't know that they're going at the same rate.
you would still get infinity minus infinity.
That's true, but you don't know it's symmetric. That's, I see what you're saying, but you don't know
But
that they're both going at the
it
same
is
rate.
the same equation. You would know this.
It goes to the Emma Harper question. What are the odds that they move exactly the same? Practically zero.
It's the same equation, so it's
Yeah, but the endpoints are different. I agree. The equation is the same, but the endpoints are different. A and B are different. A, to say that they're always the same on, that's a huge assumption. That's it. Okay, so that's it. Questions on 124? 1, did you say? Okay.
2 and 3.
2 and 3? I'll just stick with 1. Take questions from anybody else. All right, 1, cool. All right. Oh, 124. Sorry. Okay, so this is definitely one of those where I would personally do this as an indefinite integral to get the antiderivative and then bring it back. So I would say something like this, 1 over x squared plus 10, what is it? Find the antiderivative off to the side, but do it without the limits, because you don't want to get the limits into the trig sub mix. It's a mess. So I would do something like this. Did you trig sub with x equals root 10 tangent? Yeah. Okay, so this then becomes 1 over 10 tangent squared plus 10. The top becomes root 10 secant squared. I think the root 10s drop out. This becomes secant squared over root of secant squared, so it's just a single secant. Yeah?
Is that you're finding it to revolve around the x-axis?
Oh, is it a volume?
Yeah.
Was it square rooted before?
Yeah, it was.
Oh, so it's not even square rooted, right? There's a pi out front and there's no square. Oh, shoot. So, gosh, because of that, couldn't we just use our normal arctangent skills? Oh, let's do that. Okay, so cool. So this is pi. Is it 1 over root 10 arctangent of x over root 10? Is that right?
Yeah, I don't think
Something like that. Okay. Are we good?
Well, I really back in the book was
talking about
What did you? I mean, just look at your work. It might be different just by virtue of a little.
Sorry, but don't you think everyone has to actually follow my example?
You think so?
Just in general?
Just general being you?
I'm
I agree with what you're doing.
intermediate.
So they just rationalize every usage, right? You're good.
I think we just